I have a question, Professor.
Sure thing, Horace.
I was on the treadmill for about an hour, hour and a half, and I burned up 500 calories. My question is, okay, so I'm sweating, and the calories are saying I burned up 500 calories.
Hmm.
I'm just wondering, what does that mean, really? Because the sweat is pouring off me, I think, to cool the body down, and I taste salt. I just was wondering, what does that mean? I'm burning up calories, is what I was after.
Well, our bodies um, are basically nature's version of in a way of think in I'm trying to come up with a metaphor here to explain. One way to look at the human body is that it's a type of engine that requires energy to run. And if you remember from last week, I said energy is measured in calories, not wattage or amperage or voltage, nothing. It's calories. That's energy. So anyway, your recommended daily diet is approximately 2,000 calories a day. But based on what I've been reading in popular news media, my guess is most people's average daily intake is closer to 4 to 6,000. And uh, so anyway, what do you need all that energy for? Well, your body has the ability to take the sugars in your body and break it down into the energy necessary to run all the various cellular functions in your body, because your kidneys are made up of different kinds of cells as opposed to your liver, your heart, your lungs. They're unique to that organ. And so each individual cell has a function to perform, and it requires energy to do that. So what exactly are you doing by eating up these calories? Well, you're you're burning the gasoline that is stored in your body, and it's getting rid of the waste material in the form of sweat and heat that your body radiates from running on the treadmill. And so the proof that you are actually burning calories is the heat that your body gives off when you exercise. And as far as the 500 calories are concerned, um, a single, and I'm guesstimating here, a single 50-cent chocolate bar of any kind, whatever your favorite chocolate candy is, just that single bar alone is about 600 calories. So that's the equivalent energy that your body has consumed. And so if you were to combine that with a diet that is not 2,000 calories, say you want to cut it down to 1,500 calories a day, you'd probably lose a significant amount of weight within just 3 or 4 months.
So I'm walking on the treadmill. I'm too old to be running, but
Oh,
I'm
yeah.
wondering, am I not doing? Am I just wasting my time? Because if a candy bar is gonna be more, I don't really eat sweets, but whatever I'm eating, I see is loaded with calories.
The things that, a lot of people there's a lot of people, and I don't doubt there's people in this class who have experienced various weight loss programs. They've tried exercise, they've tried specific diets, and some of them worked for them, some of them didn't. So they had to shop around and find out which one of these diets works best for them. But what you're doing, Horace, is perfectly acceptable. Unfortunately, too many people think that if they have to start exercising, boy, they just got to jump in the deep end and just go for it and play at professional level. Well, that just ain't happening. So you're doing it the right way. You're not pushing your body excessively hard. You're building up, because if you keep it up, Horace, within a matter of months, you're going to be walking a little longer. You're going to be walking a little further. Next thing you know, you're going to say, "Oh, forget the treadmill. I'm going outside and walk." That's how it's going to work, and that's how it should work. But unfortunately, it's, people want to, they want to go full blast the moment they start something, and that's just not the way to do it. I used to belong to a health club, and for a long time, for like 40 years, I was a 3 to 4 week, a day a week health club guy. My thing was playing racquetball, and I played for the most part throughout those entire 40 years with the same group of people throughout that entire time. So my health club was kind of like a social club to me. Working out and sweating and exercising to me were just like added extra bonuses. I enjoyed the social aspect of it more than I did the sport itself. But today's healthcare, people's individual, routines for weight loss or staying in shape and whatnot, what I've noticed is there's a trend away from team-related activities. You no longer, you don't hear quite as much about the local softball leagues or the baseball leagues or the volleyball leagues or the basketball league. You don't hear as much about those. What you hear more of and what you see more advertisements for are things that are involved, they're solo exercises. It's just you and a stationary bike, or it's you standing in front of some latest mirror technology. You've seen those commercials where there's a mirror on the wall and there's somebody in there, a recorded message that's egging you on, come on, run faster, all this kind of stuff. There's a trend towards more solo type activities today. It's more personal. It's not team oriented as much. And for that reason, my personal opinion on this exercise that the new generation's involved in a way, I feel bad for them because while the exercise is good and I encourage it completely, no matter what it is, solo or otherwise, I merely miss the days when it was a social event, a social activity. You gathered to play softball or football or basketball. In my case, it was racquetball, and it was the same group of guys for 40 years. And the other thing I really like too is my health club served beer. Oh, that was the best. Yeah, we play 4 hours of racquetball at a time, and then sit down and drink beer. Did everybody get the handouts that I sent out about 45 minutes ago? Or at least see that they're there?
I did.
Okay. Because those are going to be the topics today. Okay. This is the usual crowd, so I'm going to get started here.
Recording in progress.
Okay. Before I get started with the lecture and material here, everybody, I want to talk about the upcoming exam 2, what the plan is for the upcoming Zoom meetings and how we're going to go about the test, okay? So here's the plan. I have received a couple of emails from students who are requesting a little bit of extra time because of either a family emergency or an obligation that they couldn't get out of, that kind of thing. And it just so happened that it worked in everybody's favor because I was thinking along those same lines. So here's the plan for exam 2, everybody. Originally, I was hoping to be able to do this on Thursday, but again, after messages from a couple of students and my own thoughts on the subject, exam 2 is going to be next week, okay? What I would like to do is send all of you the exam on Monday morning and then have you turn it in to me by Tuesday, 9 a.m. Okay, so exam 2 will be next Monday. Okay, so that I believe is July 12th. Okay. I will send you the exam and the answer sheet Monday morning. And I would like the answer sheet back by Tuesday morning at 9 a.m. Please use the answer sheet. A couple of you wrote answers on the actual test itself and sent it back to me. Okay, so please use the answer sheet. Okay, so I have not finished with the lecture material, but what the plan is I'm hoping to be able to finish this lecture material either at the end of tomorrow's Zoom meeting or toward the beginning of Thursday's Zoom meeting. Regardless of which one it happens to be, once I finish the lecture, I will cover the exam itself, point out what material it is you need to focus on and that kind of thing. All right. And answer any last minute questions. Okay. So that's the exam. I'm going to send it out to you next Monday. Okay. All right. So does anybody have any questions at all about that? All right. I finished last week with atmospheric gases, two broad categories, fixed and variable. In the fixed category, I said nitrogen was the most abundant. It was 78% of the atmosphere, and it's responsible for the sky's color blue. The next most abundant gas was oxygen at 21%. Oxygen is reactive. Nitrogen was the opposite of reactive. It was inert. Okay, inert means that it doesn't want to mix with anything. So anyway, oxygen is reactive, makes up 21% of the atmosphere. The remaining 1% is argon. It is also inert. And if you add all three numbers, that's 100%. So in the variable category, I did not give you any numbers because the gases, while they are there, are in trace quantities. So I didn't want to burden you with making notes about numbers that were 0.00000063 or something like that. They're just in trace quantities. One of them was CO2, the carbon dioxide, also known as the greenhouse gas. It is responsible for helping maintain Earth's average temperature of about 56 degrees Fahrenheit. If we had absolutely no carbon dioxide in our atmosphere, everybody, the polar ice caps would probably begin extending downward into Canada and possibly the northern states of the United States. And yet it's in trace quantities. Okay. The next one I mentioned to you is ozone. That's chemically, that's O3. It is found concentrated at the polar regions. It is responsible for blocking out much, not all, but much of the ultraviolet light that comes through. It's not perfect. Some ultraviolet does get through, and it's the ultraviolet light that is responsible for the sunburn at the beach, not visible light. Okay. The third variable gas was water, H2O. This is concentrated mostly over the equator. Makes sense. That's the hottest, also the wettest region on Earth. But I had also mentioned to you the importance of H2O. Believe it or not, H2O, everybody, is a greenhouse gas. It traps heat in the atmosphere just like CO2 does. If you had too much water vapor in our atmosphere, the temperatures on this planet would increase dramatically, and you would begin a snowball effect, because as it got hotter, it would continue to vaporize our oceans. And of course, the atmosphere would be full of water vapor. And that's a greenhouse gas. It would trap heat. So anyway, the reason it's concentrated over the equatorial region, because, well, that's the equatorial region. It gets 90-degree sunlight. It's the hottest, wettest place on Earth. But We do have humidity throughout the entire planet. It's just most concentrated at the equator. And as you move toward the polar regions, it just gets continually drier and drier and drier and drier until you get to the polar regions, everybody. The North and the South Pole are the driest places on Earth, not the Sahara Desert or the Mojave or the Gobi Desert, none of those. The polar regions only get about 3 inches of precipitation a year. You get 11 inches in Visalia and the Hanford area. The only reason there's so much snow and ice located at the polar region, everybody, is because the temperatures are cold enough, it just doesn't melt. You're looking at millions and millions of years of accumulation of snow and ice. That's all. So anyway, water was the third variable gas. I also related it to the fact that it would be physically impossible for human beings to breathe bone dry, zero humidity air for an extended period of time. It would literally dry your lungs out to the point where your lungs would not have any more elasticity. They wouldn't bend as easily anymore. And you would end up having to work really hard just to breathe. And so eventually your end would come from respiratory failure if there was absolutely no moisture in our air. So you do have to have water in our atmosphere for a variety of reasons, and that's just one of them. So those were the three variable gases: CO2, O3, and H2O. Okay, and that's where I left off last week. I sent you some handouts prior to the class today that had to do with atmospheric pressure and adiabatic lapse rates. I understand that many, if not all of you, are not familiar with the terminology here, but rest assured I will explain it to you, so please don't be intimidated by it. What I want to start with are pressure systems, okay? First, before I begin this section of material, everybody, if you really want to understand or get a bird's eye view of all of this, you have to imagine in your mind's eye, everybody, you have to be able to stand outside the earth and look at the relationship of the sun and the earth and how the sun affects the earth and ultimately its weather. Keep in mind, it's continually shining down on our atmosphere, continually. And as the earth rotates, a different side of the earth faces the sun. The other side that's in darkness, we call that night. Now, what I'm getting at is that the sun is shining down on us 24/7. And because the earth rotates, as the sun is pointing towards the earth is rotating underneath that. And so a different area of the earth gets really intense amounts of solar radiation, over and over again as the earth rotates. Well, as that energy heats up the atmosphere, it's going to create differences in air pressure. Now, here's what air pressure is. This is a definition, everybody, and you will have to know this. Here on this earth, everybody, air pressure is the weight of the air over your head resting on you personally or the surface of Earth. That's air pressure. It's the weight of the air that you are breathing. Our atmosphere is 70 miles thick. Relative to the size of the earth, that is damn thin. But it is 70 miles up. It thins out very quickly. And what I mean by that, if anybody in this class has hiked up in the Sierra Nevadas, once you get up to 8,000 feet or above, depending on what kind of shape you are in, you start to notice that it's harder to breathe because the air is getting thinner and thinner the further up you go. So even though our atmosphere is 70 miles thick, it thins out very rapidly, so that by the time you get to 18,000 feet, that's only 3.5 miles. The atmosphere is 70 miles thick. But once you reach the 3.5 mile mark, now the atmosphere only contains about 50% of the original oxygen. This is why it is so hard to breathe the further up the mountain you get. Okay? So I'm about to give you 4 different numbers that essentially represent the weight of that 70 miles of air that is covering the surface of Earth, of which you, me, and everybody else are effectively bottom dwellers at the bottom of an ocean of nitrogen and oxygen. We're like, what do they call those bottom feeders in those lakes? That's kind of what we are. Anyway, atmospheric pressure can be represented by 4 different numbers. All 4 of these numbers, even though they're different, are equal to what is called 1 atmosphere of pressure. Okay? So all the numbers I'm about to give you equal 1 atmosphere of pressure. The weight of the atmosphere was not officially and accurately measured until the late 18th century. It was somewhere around the 1790s that it was first accurately measured. And the device that they used, obviously technology has improved upon it, but it's essentially the same principle that was used in the 1790s. But suppose for a moment you had a petri dish and you filled it with liquid mercury. And you did this in a vacuum, okay? The petri dish full of mercury is in a vacuum. And then you stand in the, not you, you place a glass tube that is closed on one end and open on another. And you place the open end in the center of your petri dish. And the mercury, what you do is you open the doors to the vacuum and you allow Earth's atmosphere to now fill that room. That air that comes rushing into the room is going to push downward on that mercury in the petri dish. And because you placed a glass tube in the center of that petri dish, the mercury will climb up that glass tube. And you have marked that glass tube in both standard inches and metric millimeters. You've got inches on one side of the glass tube, and you've got metric measurements, millimeters on the other side of the glass tube. When normal sea level atmospheric pressure pushes down on that mercury, it's going to be equal to 29.92 inches of mercury. The equivalent metric number to that is 760 millimeters of mercury. So if you happen to be in Europe and you're watching the 6 o'clock news and the weather guy comes on and he tells you that today's air pressure, he's going to give it to you in the metric system. So he's going to say something like it's 755 millimeters or it's 762 millimeters. Here in this country, we give it in inches. The 6 o'clock guy always says the air pressure outside is 29.92 inches of mercury. Now, be honest with yourself. How many people in the viewing audience do you suppose really understand what 29 inches of mercury means? Probably none of them. Well, now you do. 29.92 inches of mercury is equal to 1 atmosphere of pressure. It's equal to the weight of all that air over your head. The equivalent number is 760 millimeters. There's a third number I want to give you that is also equivalent. It is typically only used under laboratory conditions. You don't typically see people use this form of the number in casual conversation. The basic unit of any measurement of pressure is a bar, barometric, get it? Pressure. And so in a laboratory setting, 1 atmosphere of pressure is equal to 1013.25 millibars. 1013.25 millibars. That is the equivalent of 1 atmosphere of pressure. Sometimes you will see the 6 o'clock news guy use that term, but once again, how many of the viewing audience, be honest with yourself, really knew what the heck he was talking about? All you cared about was, is it going to rain or is it going to be sunny? Well, now you know. 1013.25 millibars is 1 atmosphere of pressure. Now there's a fourth number I want to give you, and it's a number I think most of you can more easily relate to than mercury or millibars. The weight of the entire atmosphere on your body is the equivalent of 14.7 pounds per square inch. That is what is being pressed upon you standing on the surface of Earth. You have no sensation of that pressure because your body is pushing outward with the same amount of pressure. So you don't feel anything. When you were children, did anybody ever get sucker punched? Somebody got gut punched and got the wind knocked clean out of them? Your lungs are now completely empty of air. So now all of a sudden the pressure inside your lungs is 0. You remember that really awful feeling you had in those first few seconds when the wind was knocked out of you? Now imagine that happening to your entire body. That's the weight of Earth's atmosphere. Okay, so it's 14.7 pounds per square inch is equal to 29.92 inches of mercury, is equal to 760 millimeters of mercury, and is equal to 1013.25 millibars. Okay. Some of you who have had a chemistry class may recognize that number of 1013.25 millibars. Whenever chemists perform experiments and they want to confirm a finding, they have to perform the experiment in precisely the same manner as the original. That's called duplication. It's an accepted method of testing whether or not something actually works. So you get several different groups of people that test whatever this is under the identical conditions. This will confirm the validity of the hypothesis. However, in this particular case, you want to keep the same unit of measurement here. So by the use of millibars, in chemistry, they call it 101.325 kilopascals. It's a type of unit of measurement of pressure. And so whenever a chemist wants to duplicate an experiment, he has to do so under what is called STP conditions, standard temperature and pressure. So the pressure, whatever this test is you're going to do, you have to conduct it under a certain pressure and a certain temperature every time. That will validate whatever the theory is or invalidate it. But here's what you need to know. All four of those numbers are equal to 1 atmosphere of pressure. You personally can maybe tolerate 2, possibly 3 atmospheres of pressure. At 2 atmospheres of pressure, everybody, your eardrums would probably pop. But have you ever noticed that when you drove to the Los Angeles area or further south, you had to drive over to Tehachapi? And as you went up over the mountain, did you notice that your ears popped? Because even though the top of the mountains is only 7,500 feet, you were on the valley floor, which is only about 300 feet above sea level. So you climbed over 7,000 feet, and the air pressure outside of you began to decrease. But the pressure inside your head stayed the same. Wind is created by differences in air pressure, everybody. And wind only moves in one direction, from wherever it's higher pressure toward wherever is lower pressure. So the inside of your head, relatively speaking, is now higher pressure than the air around you because you're up on Tehachapi Pass. So your eardrums are going to push outward and they're going to feel stuffy to you. And so are your sinuses. And so when you drive back down the other side of the mountain, you can feel your eardrums pop again. So air pressure, you're pretty sensitive to it. You may not know it, but your body is very sensitive to changes in air pressure. There's an old wives' tale about grandpa being able to predict bad weather because of his knee. Have you guys ever heard that story? Grandpa probably has some form of arthritis and he's got some swelling and some fluid accumulation on his knee. So it's a little poofy, okay? Well, when bad weather strikes everybody, it is typically associated with low pressure. And you see the inside of his body is still pushing outward at the same normal pressure of 14.7 pounds per square inch. But the air pressure around him began to decrease. So his knee expanded and got a little bigger. And he told the family, it's gonna be bad weather. And he was right. Okay. So that's sea level air pressure. There are 2 categories of air pressure. It is either high pressure or low pressure, okay? And one of the pages of the handout that I gave you looks like this. This is the one I'm going to reference. Keep in mind or remember, everybody, wind only moves in one direction, and that is from areas that are higher toward areas that are lower. Before I explain the diagram, the highest air pressure ever recorded on Earth was 1031 millibars. Remember, 1013.25 was normal sea level air pressure. The highest pressure ever recorded was 1031 millibars. The lowest pressure ever recorded was 905 millibars. So that's about the range in change in pressure. It's if you look at the numbers, everybody, it's approximately a change of about 150, 160 millibars between high and low. And that does not sound like a lot, but it is, okay? Because the greater the difference between the two pressure systems, if one of them is, say, 1025 millibars and the other one is, say, 980 millibars, that's going to be a hell of a wind, okay? So if you look at the diagram, everybody, I have high pressure on the left and low pressure on the right. Now, underneath those are some characteristics of each of these pressure systems. There will be a couple of questions on each of these characteristics. So here's a quick rundown on these characteristics. Number one, I'm looking underneath high pressure. Number one says rotates clockwise in the northern hemisphere. Notice it says northern hemisphere. Once you go down south, everybody, this high pressure system rotates in a counterclockwise direction. So over Australia, high pressure systems rotate counterclockwise. I'll explain why that is in just a minute. But anyway, descending air. This is air that is falling down on top of you. And yes, that is possible. Cold air doesn't like to float, everybody. It likes to sink. And so it's going to fall down on top of you. Okay. So descending air is associated with a high pressure system. Divergent air. If you look at the two arrows at the bottom of the high pressure diagram, do you notice they're both pointing outward away from the center? That is diverging air. So diverging air is associated with a high pressure system. And then lastly, it says associated with sunny days. Typically, high pressure systems are associated with clear sunny days. So what system do you suppose is over the Great Central Valley right now? High pressure. On the right-hand side of the diagram, you have low pressure, okay? In the northern hemisphere, it rotates counterclockwise. Over Australia, it'll rotate clockwise. This is ascending air. This is air that is rising. It is convergent air because if you look at the bottom of the diagram, the line appears to go towards each other and then up. That is convergent air. And then lastly, it says low pressure is associated with rainy, cloudy days. You have warm air that is rising. As it rises, the temperature will decrease. Once the temperature starts to decrease, water vapor will condense backwards into a liquid, and then it will rain on your head. So what pressure system do you suppose dominates the Central Valley in the winter time? Low pressure. Now it says at the beginning there that it rotates counterclockwise in the north and then clockwise in the south. The same thing's true with a high pressure system. It rotates clockwise in the north, but counterclockwise in the south. And the quick answer is, which I'll explain further in a few minutes, the quick answer is it's due to Earth's rotation. I'll explain why that is, but it's Earth's rotation that is causing that, okay? High pressure systems go by another name. They are also called anticyclones. Low pressure systems are called cyclones. Okay. Also, within that same handout, everybody, I did write those 4 numbers down for you, okay, in this particular diagram. I'm not going to go over this because I already did, but it's there for you nonetheless. And this is the page I'm going to be going over right now, the one that looks like this, okay? So on top, it says true wind speed, true wind direction. And the first one, there's 3 ingredients that determine true wind speed and true wind direction. Because keep in mind, you have to remember, wind still only moves in one direction, and that is from high toward low, okay? I have a real quick analogy here for you to get you to remember this, everybody. And it has to do with my asking you earlier if anybody had ever been sucker punched before. Well, you see, the bottoms of your lungs are attached to what's called your diaphragm. And there's a series of ligaments that connect the bottoms of your lungs to this diaphragm. When you take a breath, what you are in fact doing is contracting that diaphragm. The act of contraction is going to pull those ligaments and it's going to stretch your lungs. And here's why that's important. At any given moment in time, everybody, your lungs are never completely empty of air. There's always air in your lungs, even when you exhale. So on any given moment, there's approximately, your lung volume has probably 1/4 of the amount of air sitting at the bottom of your lungs. So it's about 1/4 full. When you take a breath of air and stretch those lungs down, you've increased the volume of your lungs by the act of stretching them. Now, instead of your lungs being 1/4 full of air, because you've increased the volume of your lungs by breathing, your lungs are now, relatively speaking, only full by 1/8. So the air outside your mouth is going to want to rush inward to fill in that extra 1/8. And that's a breath of air. That's how you breathe. Differences in air pressure. Okay. So anyway, when it comes to pressure gradients, this is the numerical difference between pressure systems. So like the example I gave earlier, keep in mind 1013 is about average sea level air pressure. Well, suppose you have a high pressure system of 1020, and then you have another pressure system that is 960. Wind is going to move from 1020 toward 960. That's how that's going to work. And the greater the difference between those two numbers, everybody, the faster the wind speed. You've heard of hurricanes that were categorized according to wind speed, and they were called F1, F2, F3, and then 4 and 5. If you ever remember seeing that on the 6 o'clock news. Well, a storm becomes an F1, which is the smallest category or the slowest category. It reaches F1 when the sustained wind speeds are 70 miles or greater, 70 miles an hour. There's not too many people that can stand against a 70 mile an hour wind. You just can't do it. And once you start getting up into 100 mile an hour winds, everybody, you're talking about flipping cars down the street, okay? So the greater the numerical difference between the two pressure systems, the faster the wind speed. Now, the example that I gave you was 1020 and 960. Pressure systems are relative to each other. Don't assume that anything less than 1013 is automatically a low pressure system, or anything above it is automatically high, because there does exist every day two pressure systems. One of them is 1040 millibars, or excuse me, 1020 millibars. And the one next to it is, say, 1010 millibars or 1000 millibars. They're both, well, let's say 1010. They're both slightly at and above what I considered normal sea level air pressure. So you can have, say, a 1025 pressure system next to a 1015 pressure system. The 1015 is the low pressure system by comparison. So wind is going to move from 1025 toward 1015. Okay? So don't assume that just because it's below 1013 automatically makes it low and above makes it automatically high. That's not always true. Okay, so that's pressure gradient. Coriolis effect. This is what determines the direction of if it's clockwise or counterclockwise, the Coriolis effect. It's caused by Earth's rotation. If you happen to have the ability to stand at the North Pole and look down toward the equator, everybody, if you threw a baseball at somebody standing at the equator, you're going to make an attempt to throw that ball straight at them. However, the Earth is rotating underneath you. So even though you threw the baseball directly at your friend who is standing on the equator, okay, the Earth will have rotated underneath the ball before it reached the equator. And the ball is going to appear to have been deflected to the right. If you're standing at the North Pole and you throw a baseball straight at your friend standing on the equator, your friend will continue to rotate with the Earth, and he will thus move by the time the baseball gets to the equator. and the baseball will look like it has been curving to the right because of Earth's rotation. So in the northern, this is what you need to know about the Coriolis effect. In the northern hemisphere, it deflects wind to the right. In the southern hemisphere, it deflects wind to the left. And this is why cyclones and anticyclones rotate in different directions depending on if you're in the north or the south. So the cyclones, or we call them twisters, that strike the heartland of America, say Kansas, Nebraska, that kind of thing. Those things rotate to the left, everybody. They rotate counterclockwise. So the next time you watch a movie about a twister or a hurricane, notice that it should be rotating to the left. If not, they got it wrong. If you film that very same phenomenon in Australia, then it would rotate to the right. The cyclone would rotate clockwise. Okay, but up here in the north, cyclones rotate counterclockwise. So we call them cyclones, and the generic word that we use in the 6 o'clock news is hurricane. As I mentioned to you earlier, the hurricanes that strike the southeast United States originate over the Sahara Desert. You have hot air passing over warm water, so there's your energy source, but it's going to rotate to the left. So if you ever see those satellite photographs of a hurricane that's about to strike the southeast United States somewhere, if you pay close enough attention, you'll notice that it's rotating to the left. That's what it should do because it's in the northern hemisphere, okay? And as I said earlier, everybody, the longer a hurricane sits over an ocean, the bigger it gets. That's why we don't like it when we see satellite photographs that show that the hurricane has somehow come to a stop over the ocean. That's bad because it gets bigger and bigger and bigger, okay? So anyway, Coriolis effect to the right in the north, to the left in the south, okay? The last one was friction force. This is the difference between air passing over water and air passing over dry land. Air passing over water, the air has no resistance. There's nothing to slow the wind down. There's no mountain ranges. So the wind over an ocean can be quite fast because there's nothing to slow it down. So dry land slows wind down. It acts like a speed bump. In the case of the United States, everybody, we are in a band of wind known as the westerlies. Wind is named according to where it's coming from, not where it's going. And the reason for that is wind brings weather with it. So, you know, here in Central Valley, if the weather guy wants to describe to you what tomorrow's weather is going to be like, they take satellite pictures of what the weather off the coast of California is. And in 24 hours, the air that was, say, 100, 150 miles off the coast of California is now over your head. So they take a look at a picture of the ocean. And they say, oh, that's going to be over our head in 24 hours. So I'm going to go on 6 o'clock news and tell you tomorrow's going to be a sunny day, 110 degrees. Rock on. Okay. So that's how that works. So anyway, friction force slows wind down. Think of it this way: when the air passes over California and then it has to pass over the Rocky Mountains, okay? All of those irregular features that are associated with the mountains and whatnot, it's the equivalent of having a stream flow by. Let's just say, for instance, you got a nice, flat, even bed, you know, nice and level, and then you got water flowing over it. It would just look like a flat stream to you, almost look it would almost look calm to you because there's no ruffling, there's no bubbling, no roiling of the water, anything like that. There's nothing slowing the water down. So it's just rushing by you, minding its own business. Now, all of a sudden, throw a bunch of big rocks in there, and you're going to slow the water down, but you're going to create all these eddies and currents off to the side of the rocks. This is what the mountains on dry land do to the air as it passes over it. So you have all these different weather patterns because of that. Okay, it's creating turbulence in the air. And the turbulence is enough, everybody. Have you ever noticed that when you flew a commercial airliner, I don't know if you guys are aware of this, but they fly roughly at an elevation of about 30 to 33,000 feet. And there's a reason for that. Not only does the jet fly more fuel efficiently, and it gets you to your destination a little faster, but the tallest mountain peak on the planet is 29,000 feet. That's Mount Everest, everybody. Once you get above 29,000 feet, the turbulence created by all these mountains is not there anymore. It's fairly calm air. So flying at 33,000 feet is also a lot smoother than flying at a much lower elevation. All right, so that's it right there. Does anybody have any questions up to now? Okay, I'm not going to ask you any problem-solving questions, so don't worry about that. When it comes to this diagram here, Earth belts, everybody, this will be the last topic for today, and then that'll be it. I gave you the names of the various belts that are located on Earth. And notice that the equator is a low pressure system. In general, it's a low pressure system because you have sunlight beaming directly down on the equator. You've got all this hot air that wants to rise. That's a low pressure system. Rising air is low pressure. Then you have the northeast trade winds and the southeast trade winds. Much of Mexico is located in the northeast trade winds, and it's the biggest reason why much of Mexico is a desert. Because you remember, wind brings weather with it. Well, take a look at a map, everybody. What is directly northeast of Mexico? Dry land. We call it the central United States. So when it passes over Mexico, it has not had time to pick up enough moisture out of the Gulf of Mexico. So you have a desert. The United States is in the westerlies. Once again, it's named by the direction it's coming from. And then, of course, you have the polar easterlies. So notice that the north and the south are basically a mirror copy of each other. The only difference is the name of northeast and southeast. Okay, but that should make sense to you, okay? Also notice, everybody, that I wrote on the equator, it says low pressure. The northeast trade winds going from the equator towards the polar region, you've got a pattern of pressure systems. And I'm not going to ask any questions on this. However, if you start from the equator and you work your way toward the polar region, it goes low pressure at the equator, high pressure, low pressure, high pressure at the polar region. The two polar regions, everybody, are the driest places on Earth, not the deserts. Why? Because they're a high pressure system. You are currently in a high pressure system. When was the last time you felt humidity in the air? You didn't, or because it's there, but it's so low you don't perceive it. You go to the North Pole, everybody, and it's a lot drier than what you're experiencing right now. They only get about 3 inches of precipitation a year. And as I mentioned earlier, the only reason there's so much snow and ice up there is because the average temperature at the polar region is 32 degrees Fahrenheit or 0 degrees Celsius, which is the freezing point of water. So the snow that falls at the polar regions just never melts. And so once again, you are looking at millions and millions of years of accumulation. This is why we spend so much time and effort at the polar regions in scientific research, because you are aware of the fact that paleontologists, when they're looking for dinosaur bones, they can roughly estimate the age of the dinosaur based on the level that they found it at within the soil. In other words, how deep did they have to go to find it? The deeper they had to go, the older it is. Well, the same thing's true with the ice. You want to know what the Earth's atmosphere was made up of 50 million years ago? Well, you dig about 2,000 meters into the ice and you pull up a sample of the ice that formed 50 million years ago, because when it formed, everybody, it trapped air in the ice. And it also trapped any chemicals that may have been in the atmosphere at that time. So we can tell you with pretty good certainty that Earth's atmosphere has not always been 78% oxygen, 21%, or 78% nitrogen, 21% oxygen, 1% argon. If you go too far back in time, everybody, our atmosphere is poisonous to you. It's not always been breathable to humans. And so the other interesting side note to this content of our atmosphere, everybody, our atmospheric content is 21% oxygen. And take a look at the average size male and female on this planet. Okay, got a mental image of that. All right. Well, look at the musculature on the average size male and the average size female. And the same thing's true of any other animal species. Take a look at their musculature. Look at how physically large they are or not are. And then you've seen the Jurassic movies. Those animals are very large, are they not? And they've got very, very big muscles. It's going to take more than 21% oxygen for those muscles to continue to function. So during the age of dinosaurs, everybody, there's not a whole lot, but there's some evidence to indicate that Earth's atmosphere, the oxygen levels were up to 35%, because at 21%, you cannot support musculature as large as the Brontosaurus or the T-Rex or any of these other animals. So the atmospheric content, the chemical content of our atmosphere has not always been the same. Right now, we are discussing the possibility of greenhouse gases and man's contribution to the greenhouse gases. Yes, I do believe we are contributing to them. However, the exact magnitude of our of our effort or our contribution to the greenhouse effect is still unknown precisely. Something I can tell you with relative certainty. Back in 1991, a volcano erupted in the Philippines. It's called Mount Pinatubo. And it was a big eruption, and it put enough CO2 into our atmosphere to equal all human industrial activity for the 20th century. A single major volcanic eruption. So yeah, I believe humans are contributing to greenhouse gases, but I can't say for certain what the exact impact is. You know, are we contributing half of all greenhouse gases, and what's going to be the impact? I don't know that. I don't think anybody does. That's why I said earlier that we haven't studied it enough. We don't, we're not precise in our information and our knowledge. That's why we are so interested in places like Venus, because it's completely covered in CO2. So we want to know, what are going to be the long-term effects of CO2 in our atmosphere? And we don't know the answer to that yet. And so that's where I get a little hesitant to say I'm for or against this whole CO2 thing, because we just don't have quite enough information yet. But nonetheless, it's going to be 115 degrees in a couple of days here. So I'm sure from our perspective, it's real. Okay, does anybody have any questions? Okay.
Recording stopped.
All right, I will pick it up tomorrow with the adiabatic lapse rates. I will go over that. I'm hoping to finish the lecture on Thursday, and I will spend time doing a review on Thursday, okay? And then once again, I will mail the exam out to you on Monday morning, all right? So otherwise, have a good day. I'll see you guys tomorrow.
Professor,
Thank you.
Bye-bye.
is,
Thank you. Have a
Yes.
good day.
are you going to have the lecture notes out today on this particular lecture?
Yeah, I will. You want a copy of the notes? Yeah, I'll send them to you, Horace.
Yeah, I can't write that fast, so I just go by your lecture and make notes.
Okay. Are you able to view the recording?
I make my notes when I view the recording.
Okay,
I slow you down and start writing the notes.
that's
then.
all right, Horace. I'll send you some notes.
Okay, I appreciate it.
Okay. Bye-bye.